Uh, Welcome back. In today's lecture, we are going to see a motivating example for a divide and conquer, and we'll give brief motivations for the whole course. Okay. So start with a simple example. Uh, so let's consider the following problem. Okay. So in this course, when we say problem, it always comes up with an input output specification. Okay. So here input are two n-bit natural numbers. Let's call them as x and y. Okay. So output should be their product. That is z is the output, where z is a product of x and y. So here we'll assume that x and y are represented in binary. Okay. So they are n-bit natural numbers. So let's take a simple example. Let's say x is 11. In binary, this is 1011. And y is 13. In binary, this is 1101. Okay. Now the output should be 11 into 13, again in binary. So in binary, it becomes this 1, 000, quadruple 1. Okay. So now the task is to come up with the algorithms for this. Well, there's no big deal. I mean, maybe from 4th standard onwards, we have seen algorithm. So I'll just go over that algorithm again. So idea from our school. So how do we perform multiplication? So I'll just go with this example. So what we do is we just make copies of the first number based on the second number. So the first number here is 1011. The second number is 1101. Okay. So we scan the second number from right to left. Okay. And we look for positions where the number is 1. So position 1, position 3, position 4. Okay. So now what we do is for position 1 of 1101, we'll put a copy of the other number, which is 1011. Now position 2 is 0, so we do nothing. For position 3, we make a copy of 1011, but with the two zeros appended to the right. So 2 is 3 minus 1. So for the position 4 of 1101, we again make a copy of 1011 with three trailing zeros, which is 4 minus 3. Now we add these numbers. Okay. So this is a binary addition. So you just look at these 3 digits, add them. 1, 0, 0. The sum is 1 with carry 0. This is 1, 0, 0. Sum is 1 with carry 0. Similarly, 0, 1, 0. Sum is 1 with carry 0. Now 1, 1, 1, 1. This adds to 3, which in binary 1, 1. So this is 1 with carry 1. So now you add the carry to this. So 1 plus 0 plus 1. This is 0 because the result is 1, 0. Carry 1. Similarly, carry is 1 here. Result is 0. Carry is 1. Result is 0. So the carry gets forwarded here. So this is the number that you get. Okay. So this is the product 143. Okay. So just to make it precise, algorithmically what we did is scan the second number, that is y, from right to left this way. For each one that is seen in y, for each one, so here there was 1, make a copy of the first number. But we'll append a suitable number of zeros. So here this was position 1, so there is 0, 0. This is position 3, there are 2 zeros. There is position 4, there are 3 zeros. Okay. And add them. Okay. So let's analyze this algorithm. This is a pretty straightforward algorithm. This is what we did in our school. But only thing is we would have done it in decimals, not binary. Okay. So binary is exactly the same, except that the digits are added in binary. Okay. So, okay. So now let's analyze the cost. Okay. So what is the primitive routine that is involved here. So one routine that is involved here is addition of two n-bit numbers, okay, or maybe at most two n-bit numbers. This will assume that it requires Cn operations, where C is a constant, okay. The C will depend on your actual computer you're implementing, but it will be a fixed constant depending on the computer. Now, since y can have at most n many ones, we may require in the worst case n such additions. So the total number of time will be basically n square times these constants. It depends on the machine. So it will be a constant multiple of n square. Okay. So or the total number of operations that you need to perform in your processor is a multiple of constant multiple of n square. So when I say constant, this constant has to be independent of this n. So what was the n? So n was the input length, that is length of these numbers. Okay. Yeah. So that means to add 200-bit numbers, you'll require a time of 100 into 100, 10,000, a constant multiple, maybe 5 times 10,000, so 50,000 steps. Okay. So the question is, can we do better? Or is this the fastest algorithm? Well, you can come up with some minor tweaks. We can say that, okay, maybe I can do by addition with, say, 1n operation or 2n operation. You might gain on this constant, but that is not what we are looking at right now. Okay, I'll tell you why later on. I mean, in the next couple of lectures, it will be clear why this kind of measure is being done. For now, we want to measure the running time in terms of n. Any constant multiple, we are happy to live with. So yeah, so in 1962, Russian mathematician gave a much faster algorithm for the same. Okay, probably this algorithm was known much before, but it was formalized only in 1962. Okay, so the algorithm is simple. Okay, so for simplicity, we'll assume that n is even. Okay, so n is odd, the algorithm will work fairly well. In fact, it's easier if we assume n is a power of 2. Okay, let's not worry about that. So let's write x bitwise. So let's say x is xn, xn minus 1, etc. x1, where these are bits. And write y again bitwise. So let's say y is yn, yn minus 1, etc. yn, y1, where these are bits. Okay, or digits. So now what we do is we split these digits. So we take the first n by 2 and call it as a. So a is a number which is obtained by writing the first n by 2 digits starting from left of x. This is the MSB of x and next MSB and so on. So first n by 2 bits, and the remaining n by 2 bits, that's the least significant n by 2 bits, we call it as number b. So similarly, we do it for y. So c is yn minus 1, etc. yn by 2 plus 1, and d is yn by 2 minus 1, etc. up to yn. Okay. So now let's do simple arithmetic. Okay. So you can see that x is nothing but 2 power n by 2 times a plus b, and y is 2 power n by 2 times c plus d. Okay. So let's now look at the product. So we'll do simple arithmetic. So xy now can be written as 2 power n by 2 times a plus b times 2 power n by 2 times c plus d. So let's expand this out. So this will come as 2 power n times c, ac, and 2 power n by 2 times ad plus 2 power n by 2 times bc plus bd. Okay, so let's call this as equation 1. So now let's watch this expression closely. Okay. So forget about this multiplication by 2 power n. Okay, it's actually not a multiplication, right? Multiplication by power of 2 in binary basically amounts to shifting, left shifting the number by so many positions. So here this is left shift of this value AC by n bit position. This is left shift of value AD as well as BC by n by 2 positions towards the left. Okay, So this operation we are not really counting on because this is not an actual multiplication. This is basically a shift operation which will require possibly n bitwise operations. Now for this expression, if we compute AC, AD, BC and BD, then with shifts as well as additions, how many additions are there? 1, 2, 3. 3 additions, we can get the value xy, right? Or in other words, we decompose the problem of computing product of two n-bit numbers, which we have represented this way, to that of computing product of how many? 4 n/2 bit numbers with some addition and shift operation. Okay, so 2 shift operations and 3 additions. Okay, so or in words, we have reduced the problem of computing xy to first compute AB, AD, BC and BD, then use 3 shifts and 3 addition operations to obtain the result. Okay, so now we can state this as a simple recursive procedure, right? So add xy. Now we make a multiply xy makes recursive call multiply AC, multiply AD, multiply BC, multiply BD. So 4 recursive calls. Each instance will have size n/2, and then shift, and then add. Okay. So we can write the time required for this algorithm. Say let's say Tn be the time required to multiply 2 n-bit numbers. Then using this, the above expression 1, we can say that Tn is at most 4 times T of n/2, which is required to multiply AB, AD, BC and BD, plus C times n, where the C is the cost that is incurred for performing 3 shift operations and 3 additions. Okay, so C times n, that's the overall cost that is incurred. So if you solve this recurrence, so this recurrence solves to some beta times n square. Beta is some constant again. Okay, so you might get frustrated that okay, I'm putting the constants under carpet. It's not really important at the moment. Okay, so let's not worry about the exact constants here. Okay, you might be able to optimize on it and so on. So let's not worry. I'll soon, in the next lecture, I'll tell why we can ignore the constants. So yeah, one thing is we'll optimize. So see, did we really gain anything? Up to a constant multiple, we didn't gain anything, right? We still require n square operations. Our high school idea itself required n square operations. So we didn't really gain anything. Now, but of course, nevertheless, it's a new idea. It's a completely different idea. So it's worth exploring. Now, the first question is, will the improvement on C be of any use? Well, I didn't tell you how to solve the recurrence though. We will be discussing it soon. But modulo the solving recurrence, we can easily see that changing C, even if you make this as half or 1/4 or whatever, this won't really improve. Okay, so the n square will, as long as there is a 4 here. Okay, so what Karatsuba noticed is if you reduce this 4 to some value smaller than 4, this certainly improves the running time. Okay, so that's exactly his attempt was. Okay, so what he did was he did a simple reorganization. Okay, so Karatsuba's idea was the following. So we want xy, which we wrote as this product. I mean, using the notations for A and B. Now, expanding this is what we got. So we required 4 multiplications of n/2 bit numbers. Now, instead, he did a clever reorganization of this. Okay, he just wrote this as, so 2 power n minus 2 power n/2 times AC plus 2 power n/2 times A plus B times C plus D plus 1 minus 2 power n/2 times BD. Okay, so let's expand out this expression. So here we have 2 power n into AC, that is what is required, and we have BD, that is required. Now the rest should add up to this. So let's see. So AC has a 2 power n by 2, which is correct. BC, sorry, AD has a 2 power n by 2. So similarly, BC has a 2 power n by 2, which is correct. The remaining things should cancel out. So what are the remaining things? I'll be getting AC into 2 power n minus 2, but I have minus 2 power n by 2 times AC, which gets cancelled. And another useless factor is BD, sorry, not BD, AD. Yeah, so another factor is, so I have 2 power n by 2 times BD, which again is cancelled here. So I wanted BD, so BD I have got here. Okay, so you can see that this expression simplifies to this expression. It's the same expression. But what is the advantage of this expression? Let's just stare it again. So with the two addition operations, okay, I can reduce the task of multiplying two integers into computing a product. Again, this one, so a plus b, so a and b are n by 2 bit integers, right? A plus b will be n by 2 plus 1 bit integer. So c plus d again will be n by 2 plus 1 integer, bit integer, right? So this will be a product of n by 2 plus 1 integers of n by 2 plus 1 many bits, and this again product of n by 2 many bits, product of integers of n by 2 bits. So I have how many products now? One product, 2, 3. Okay, so what we have done is, so multiplying x and y is reduced to 3 multiplications of n by 2 bit numbers. There's a small catch. In fact, a plus b and c plus d are not n by 2, n by 2 plus 1. Okay, let's ignore it for a moment. Okay, not a much big deal, as we'll see later on. Okay, followed by how many additions? 1, 2, 3, 4. 4. I wrote it as 5, but 4 additions and 2 subtractions, and how many shift operations? 1, 2, 3. 3 shift operations. In fact, 4 shift operations. Okay, it should be 4, not 3. Okay. So now modifying the recurrence now. So the revised recurrence will be Tn less or equal to 3 into T of n by 2 plus some constant times n. Okay, so this constant depends on these operations. Addition, for 5 addition, 4 additions, right? 4 additions, 2 subtractions, 4 shift operations. Okay. So yeah, did we make any gain? Yes. So if you solve this recurrence comes down to, so T of n is at most some constant, I wrote it as beta prime, times n to the log of 3 to the base 2. Okay, which boils down to a constant times n to the 1.59. So if you look at this expression, this is much better than n square, right? Significant improvement. So n to the 0.41 improvement, right? Particularly if you have, say, n is 1 million, this is significant improvement here. Okay, so yeah, so just make it precise. So let's write down the algorithm. So the algorithm is simply as follows. So input two n bit numbers x and y. So output should be their product. So first step is you write x in this form, y in this form, by taking the first n by 2 bits and representing it as number a, the next n by 2 bit, that's the least significant n by 2 bits as b. Similarly for y, c as c and d. Now recursively compute AC, a plus b into c plus d and bd. Now return this value. Okay, so this is the overall algorithm. The algorithm has a complexity of constant times n to the 1.59. Okay, so yeah, so now, so what is the message? So this simple idea of dividing the input and then expressing our resulting outcome in terms of this divided input actually was fairly helpful. It significantly reduced the running time. Now you may ask, is this the best algorithm? No, it is not the best algorithm. So the best algorithm runs in time something like n times a small number, which is like a log n times, say, yeah, something very small, something which is a non-constant value, but we call it as log star n. Okay, so yeah, Karatsuba's idea was revised later on using more mathematical tools and so on. But for us, I mean, what we want to have a take-home message is the simple idea of dividing the input actually led us to a drastic improvement. Okay, so this is where, I mean, this is what our motivation for algorithms. Okay, so the algorithm designer's job is to come up with ideas so that your performance, so here in this case, performance was the running time. Initially it was n square up to a constant multiple, but we have reduced it to something much smaller. Okay, so algorithm designers' first task is to come up with ideas, or in other words, algorithms, or which lead to algorithms with significantly improved performance for the problem. Okay. Now we'll see in a similar spirit, we'll see another example with the not much details. Okay. So, so task is to compute a product of two n by n square matrices. Okay. So suppose we are given as input two n by n square matrices with, let's assume, integer entries for now. Output must be their product. Okay. So again, we'll do the high school definition. So we know that by definition, the product, the ijth entry for I comma j less than or equal to n, ijth entry of the product matrix is given by this expression. Okay, summation k equal to 1 to n xik times ykj. Okay, now to compute one entry of z, say zij, we require how many operations? So there are n operations here. So so n summands here. So n multiplication operation. So to have n summands, sum them up, we'll require n minus 1 addition. Okay, so we'll require a total of 2 n minus 1 operations. There are a total of n square entries in Z. So a total of 2 n cube operations. I'm taking this n minus 1 as n. Okay, otherwise this is slightly lesser than this. So hence overall running time is at most 2 n cube. Again, this has been there since the time matrices were introduced, some 200 years ago. Okay. Now the question is, can we do better? Can we do with better number of operations? Okay. So each matrix has n square entries. So n square is minimum number of operation, but n cube is sufficient up to a constant multiple. Now the question is, can we reduce it further? So yeah, so kind of motivated by Karatsuba, I mean, though it is not exactly, it's independent work. So Strassen had a similar divide and conquer approach. Okay, so Karatsuba wrote an n bit number as n by 2 bit numbers, two n by 2 bit numbers. So now Strassen did a similar thing. What he did is took the matrix. Now you just view it as 4 n by 2 cross n by 2 matrices. Okay, so the first n by 2 columns and first n by 2 rows gives me the first matrix, and the next n by 2 columns and the same first n by 2 rows gives me matrix B, and then C and D, so on. Similarly, split Y. Okay, so we have 4 n by 2 matrices for X and 4 n by 2 matrices for Y. Okay, so total there are 8 n by 2 cross n by 2 matrices. So now let's write down the product. Okay, so then you can easily see that the product basically can be written as the first matrix there, which is n by 2 matrix, will be basically AE plus BG. So the second entry will be, so this is not an entry, this is a matrix, remember. So will be similarly AF plus BH and so on. Okay. So now these are 4 n by 2 by n by 2 matrices together forming as n by n matrix. Okay. So let's do a cost analysis. So now computing Z can be reduced to computing these products, that is AE, BG, AF, BH, CE, DG, CF and DH. So how many? So 8 products of n by 2 by n by 2 matrices. So this gives us the recurrence. So recurrence will be, so suppose Tn is the number of operations. When I say operations, additions and multiplications for computing product of 2 n by n matrices, then Tn is bounded by 8 times T of n by 2 plus this. So what is this? So this is required to this is the time required to retrieve. So basically addition of n by 2 matrices. Okay, so that is it. So you can see that any n by n matrix can be added in time n square, right? So now the recurrence is Tn less than or equal to 8 into T of n by 2 times C of n square. You'll see that this recurrence really does not change anything. Okay, so this recurrence basically gives us the same value. So this solves to, I didn't write it down here, this solves to order of n cube. So Strassen was experimenting with something, and in fact Strassen was trying to prove that n cube is the minimum number of operations required to multiply two matrices. So he suddenly came across this expression, and he realized that you can reduce this value 8. So instead of computing this 8 products, you can reduce it to computing 7 products. Okay, with the very, very cleverly formed equations on or expressions on these matrices. Okay, I'm not writing down those expressions. So now once we replace this 8 by 7, this drastically improves the performance. Okay, so and Strassen showed that this recurrence can be solved to Tn is equal to beta times some constant times n to the 2.81. Okay, so this is an improvement compared to n cube, right? So again, the idea was very similar to Karatsuba's in the sense that you divide the matrix into small submatrices. But the clever part, we'll soon be seeing the full details of this when we have a bit more formalisms set up. We'll see that this was really out of the box. Okay, it was seriously, I mean, you won't understand it at all. Though later on mathematicians figured out that there are deeper mathematical ideas behind it, but while inventing it, Strassen had no idea. So he just somehow cleverly came up with it, or would say accidentally came up with it. Okay, so yeah, the main message here is algorithm design is so crucial. I mean, in the sense that the ideas that we come up with can make drastic improvements on the performance of algorithms. Okay, so yeah, so I have another 10 minutes or so. Yeah, so for the rest of the lecture today, we'll just quickly see, so what kind of analysis or what kind of study of algorithms we are going to do. Okay, so yeah, the first thing is, so let's just compare the two examples. Okay, in the first example, we said the running time is n to the 1.59, okay, which is the total time required. Whereas in the second example, we said n to the 2.81, but unfortunately, it's not the running time. It is the total number of operations. It's not the time. So here we are assuming that each each entry, right, multiplying or adding them takes unit time. Whereas it could be, I mean, so multiplication itself, it requires so much of time. So in overall time could be this times this. So 2 to the n to the 2.81 times n to the 1.59, right? But it's okay. I mean, in the sense that the point is the two models are different. Okay, so the performance measure depends on the underlying model. For the first example, we consider the bit model where addition of two numbers requires n bit operations. Whereas for the second one, we consider the word model where addition and multiplication of arbitrary integer is considered as one unit operation. Now you may ask, okay, what is the right model? Tell me the right model. I'm totally confused. So here, I mean, in this first part, we are really interested in, I mean, see, if you just take multiplying to n bit integers as a unit time, right? The model is useless there, right? So we wanted to do a more detailed analysis of the running time that is required, okay? And so that is why we had to consider bitwise operation. Whereas in the matrix multiplication, okay, of course, had we considered this bitwise operation too, so the corresponding multiplicative factor would have been there. But the intrinsic difficulty of the problem is not about multiplying or adding integers. The difficulty lies in the property of matrices. So that is why we just put the multiplication and addition tasks as unit operations, okay? So this model is kind of justified. But when you say precise running time, I have to put the corresponding multiplicative factor here too, okay? So that is something that we need to keep in mind. We'll make a precise definition of the model in 2 lectures from now. Okay, so what kind of models we are considering and so on. But we need to keep this in mind. Okay, so the underlying model is important. Okay, so now we'll just quickly see what is the main task of an algorithm design. Okay, an algorithm designer designs algorithms, in fact, which is in fact a creative activity. Not only that he designs algorithm, he should prove correctness of the algorithm. That is, he should say that for every input, the algorithm works correctly. That is, it gives the correct output. In addition to that, the algorithm designer will have to prove performance guarantees, give proof of performance guarantees. So when I say proof, it should be a mathematical proof. Okay. So it could be in terms of running time or, sorry, ignore this word. So it may be running time or number of operations, or it could be memory used, whatever. Okay, it depends on the application. It depends on the actual problem. Okay, so these are the primary tasks. So for these tasks above, so what I'll say, I mean, subtasks will be: one is the design of the algorithm, coming up with an algorithm idea like Karatsuba or Strassen did, and then analysis of the algorithm. This is the important part, okay, as important as the design. This involves a detailed understanding of the working of the algorithm to prove the correctness and performance guarantees, okay. So in this course, our aim is to develop mathematical and intellectual tools for design and analysis of algorithm, develop various approaches for algorithm design, and give concrete examples with detailed analysis. So these tools will be built with concrete examples. We'll study particular problems and develop algorithms, maybe different kinds of algorithms for the same problem, and we'll analyze them. And along the way, we'll be developing tools which will be useful for you in future. Okay. Yeah. So this is a justification. Why do we have to do such a tedious process? See, I mean, most of you are programmers. You write programs, right? I mean, programming is nothing but designing algorithm and implementing it, right? So why can't you just sit and write programs? Why do you have to go through this tedious process? Why do you have to learn math and know how to prove correctness and so on? So these are some of the usefulness of going through this tedious process. One is, once you have performance guarantee, right, of an algorithm, you can use that algorithm as subroutine anywhere without worrying about the correctness. See, whereas a program, right, you would have proven, I mean, you would know the correctness of the program only on the examples that you run, only on the sample inputs you have run. Whereas once you have a performance guarantee, you know that the algorithm runs on all inputs, right? So then you can use it as a subroutine anywhere without really worrying about the context. Otherwise, it may happen that for that context, that particular input, your algorithm, your program is not working. Okay. So similarly, another factor is scalability. So with our kind of analysis, the algorithms scale. You don't have to worry about the input size at all. It works for, when we say the algorithm is correct, it works for all inputs. Okay. So whereas a program typically is tested for only a fixed set of inputs. So that is a problem with this simple program approach. Okay. And other advantages are improvements. It's easier to improve. I won't really get into the details of it. And the model, the kind of analysis that we do is completely motivated from complexity theory. Okay, complexity theory is a sub-discipline of computer science where the ultimate objective is to classify problems based on resource requirements. Okay. Yeah, so that's it for today. Yeah, it's already time. In the next lecture, we will set up some basic apparatus like big O notation and so on. We'll also give clarity on the models, and we'll start with some sample tasks like proving lower bounds and so on. Okay, so that's it for today.